Good afternoon, ladies and gentlemen. So this is the second video that kind of wraps up, hopefully, most of rotational motion. So this is kind of a continuation of talking about torque. So the first video introduced the idea of what torque was, connected it to Newton's second law for rotation. This is focusing specifically on the idea of torque and objects that are in equilibrium. All right. Now, the first half of this is actually a lab. So if you could, what I'm going to do in a sec, I'm going to explain what you're going to do, and then you're going to pause this video and go through and finish the first part, which is just the front side of this lab. All right. But you're going to click this link, and you're going to open up a sheet that looks like this. Now, on this bar is a mass that we have hung. And what we're going to do is you are going to be able to do two things. You can either change the mass of this by clicking it, or you can change where the mass is. All right. And your task is you are going to then click on the two force sensors that are holding up this bar. And I want you to kind of pay attention to what the force in the force sensor reads. Okay. Now, of course, normally what we would talk about is that if I just had a mass that was if I had two ropes holding up a mass, they would split the force equally. We're going to find out that's still the case when you have something like this. Because in theory, this rod, if I cut one of the strings, this string is no longer just going to hold it up. It's going to start to rotate. All right. And that's going to be important here. So if you could please, ladies and gentlemen, you are going to do this lab. So pause this video. When you're done, we're going to talk quickly about what the answers are because I want to get to the practice problems on the back. So work through that lab. When you're done, come back. All right, cool. I hope you are back because you are finished, not because you got bored, which of course is not the case because this is a really exciting lab. So let's answer these 6 questions real quick. They kind of came through it. So remember, the first part of this lab is you were moving around, you were increasing the mass. So you kept the mass at a certain point. Hopefully you noticed that if you kind of followed my directions, the left force sensor always seemed to have a higher reading than the right force sensor did. All right. Now, of course, as you increase the mass, both force readings seem to increase as well. And what's interesting is that one observation you could have made that was rather interesting just because of kind of the systematic part of it is that they always have the same difference in force no matter what you do to the mass. All right. So as long as you keep it at that same position and you increase or change or decrease the mass, there's still the same difference between the left force sensor and the right force sensor. All right. Now, for part 2, this time you kept the mass the same, but you moved it around kind of that bar. So in this case, depending on if you moved it, I think you moved it from left to right. If you move it from left to right, you probably noticed it at first. The left force was much higher than the right force. But as you move it from left to right, you actually start to see the opposite, that the left force starts to go down and the right force sensor starts to go up. All right. Now, when we think about it this way, what's happening to the center of mass of the object? If I'm moving that mass and I'm shifting it from left to right, I'm also shifting the center of mass, which means that in this case, the center of mass is moving from left to right. Now, the weight of the object, and this is kind of an important thing because it can seem at first it is changing, but honestly, if we keep the mass the same mass, the weight is never changing. Where the mass is changing. And we're going to find out that that is important to keeping this system in equilibrium. All right? And in this case, we're going to talk about the idea of how equilibrium we're used to talking about in terms of linear forces. Now we're going to talk today about how it connects back to rotational motion as well. All right, so with that being said, let's scroll down. Equilibrium and torque. So far we've talked about the idea of equilibrium. We've brought it up a bunch of times. We love when things are in equilibrium because it means they are not moving. And in fact, torque does not change this opinion whatsoever. Instead, what torque does is it just adds an extra way that we can be in equilibrium. All right, so when an object is in full equilibrium, that means that not only are the net forces all equal to 0, but the net torque is also equal to 0. So all the torques on the object are also equal to 0. So when an object is in full equilibrium, the linear forces are balanced, equals 0, and the net torques are also equal to 0. All right. Now, what that would look like in linear motion, so linear equilibrium, it means whatever the left forces equal right forces, or up forces equal down forces. We've done this many times, not worry about it. For rotational equilibrium, what that would look like is that all of the counterclockwise torques have to equal the clockwise torques. All right, so for rotational equilibrium, What that means is that the sum of clockwise torques equals the sum of counterclockwise torques. And we already kind of saw how we can combine, how we can like add or subtract clockwise and counterclockwise torques from the last video, all right? But we're going to practice that a little bit more today in detail. So the first question here has to do with a basket full of porcupines. So I have a basket full of porcupines, and they are sitting 1.5 meters away from a pivot on a seesaw. All right. Now, what I'd like to do is I want to place a basket that is full of picas to balance the seesaw, so it just kind of sits there in equilibrium. All right. Now, of course, a seesaw is a rotating system, so we need to make sure that in this case, to make sure it's in equilibrium, we have to keep the rotational equilibrium balanced. All right. Now, to do that, we need to think about the idea that we need to make sure that what has to be true for rotational equilibrium. And that means that the clockwise torque has to equal the counterclockwise torque. All right. So in this case, depending on how you set it up, if I have a basket full of porcupines, they're 1.5 meters away. Let's say that the way I have it set up, they're on the left side of the pivot. All right. That means they're going to produce a counterclockwise torque because they're going to want to cause the seesaw to kind of fall down to the left. So counterclockwise torque is going to be equal to the force that's providing the torque, which in this case, if I draw an FBD, you'll actually see that the force is going to be provided by gravity, the weight of the porcupines, times how far away the porcupines are from the pivot, 1.5 meters, times the angle, which in this case, FG, because this seesaw is sitting horizontally, FG makes a perpendicular angle with it, so it'll just be sine of 90 degrees. Which means right there, we have the counterclockwise torque. All right, so it's going to be the weight of the porcupines, which in this case is 80 newtons times 1.5. So it's going to be 120 newton meters of torque. Now, we know because this is going to be, we want this to be a balanced system, that means that the amount of torque the picas provide has to be exactly the same. Now, because the mass of the picas is different, that might mean we have to actually place these in a different spot as well. So for us to calculate the clockwise torque, we're going to do the same thing where we're going to do the force, which in this case is going to be the weight of the picas, and 4 kilograms is going to be 40 newtons, times how far away they are, which we don't know yet. All right, but we might find out in a sec. Times the same, it's actually going to make the same angle, so it's going to be sine of 90 because the weight is going to be perpendicular to the seesaw. So we're left with the counterclockwise torque, which is 120 newton meters, has to equal the force provided by the picas times how far away they are, which we don't know. But at this point, we do know enough that we can solve for it, and if we kind of just solve for that x, we'll get that the distance from the pivot point is going to be equal to 3 meters. All right, and right there, that's exactly how you use rotational equilibrium to solve problems like that. And what's rather interesting is that as long as you have a long enough lever, you can pretty much balance just about anything, regardless of the mass difference, as long as the lever is long enough. All right, so that leads nicely into the next question. So if I want to turn a rusty bolt, do I want a short-handled wrench or a long-handled wrench? So take a second to think about it. All right. Hopefully you had a chance to kind of contemplate on this. But if I want to turn a rusty bolt, that means I probably want to produce a lot of torque because it's probably stuck. And of these two things, the one that can produce more torque is going to be the long-handled one. All right. And that goes back to what we talked about in the last video, the idea that torque is dependent on the applied force times the length of the lever arm times the angle. And in this case, the longer wrench is going to have a longer lever arm, so it can produce more torque. All right, so you want the long-handled one. Now for the last question. So we're going to build a diving board, and the diving board setup to the left side is held by a metal rod, and it's balanced on top of a pivot point, so you can see right there in the drawing. Now, the metal rod to the left can provide 3,000 newtons of force before it snaps. I want to know what the maximum weight limit the board can support. If kids literally jump off, and I say jump off, literally this is a very boring diving board. What's the maximum weight limit this thing can support if the kids literally just walk off the edge? All right. Now remember, if we're trying to support the maximum weight, it means that the system's still in equilibrium. All right, so you want to think about how can we keep this in rotational equilibrium. All right, so I want you to pause the video here, try and work through this question. Once you think you've kind of gotten an idea, you think you got an answer, or if you're stuck, play it again and we'll see what we can do. All right. So the most important thing about this whole question, at least for the first part, is we want to make sure that the system is in rotational equilibrium. So we want to make sure that the clockwise torque is equal to the counterclockwise torque. All right. Now, since the pivot point is kind of not towards the center, but it's definitely away from both edges of the board, the metal rod and the weight of the kid are going to produce a torque. All right. Now, if we look at it, if you kind of draw the force that the kid is going to apply onto the end of the board, that means that that kid is trying to produce what appears to be a clockwise torque, which means that the metal rod is actually producing a counterclockwise torque because it is pulling against it to keep it from turning. All right. So that means for us, the clockwise torque, as we just said, is going to be produced by the kid. So it means it's going to be the weight of the kid, because that's the force that's going to provide it, times how far away the kid is from the pivot point. Looking at this, diagram, it's 1.25 meters. Times the angle that the weight makes with the diving board. Hopefully this is an equilibrium. It means it's going to make a 90-degree angle. So right there, that is going to be the clockwise torque. All right. Now, our goal is that we want to use that to figure out what is the weight that what's the maximum that this can be to make sure that this stays in equilibrium. So that means we want to kind of set it equal to the maximum torque the metal rod can provide. So this means we're going to calculate the counterclockwise torque. It says the maximum force the rod can provide is 3,000 newtons, so we're going to need to use that when we calculate the torque. Gives us the distance, once again, 0.75 meters. This force is pulling straight down, so it's perpendicular to the board, so it's going to be sine of 90 degrees. All right. Which means now we're left with just kind of a simple, you're simplifying it and solving for stuff. So we know sine of 90 is 1. So that leaves us with the weight of the kid. We don't know. The max weight is just going to be equal to how far away the kid is from the pivot point, which is going to be equal to the counterclockwise torque, which is 3,000 times 0.75. So when you go through and calculate that, you should get that that is about, I believe, 2,250 Newton meters of counterclockwise torque that can be provided. So once we know that, it just comes down to solving for FG. So if we go through and do that and get FG by itself, we get that the max weight that a kid can have is going to be 1,800 newtons. All right. And all we're doing here, ladies and gentlemen, is we're just using the idea of net torque. All right. And kind of equilibrium. So even though it's a slightly different, slightly stranger looking problem, it's still equilibrium. So same deal. I want you to answer this last question. Now we have a kid who's actually jumping off the board. So they're pushing down on the board besides just walking off. All right. So we want to know if this kid is going to cause the metal restraining rod to break. All right. And what we do here is we just think about the fact that we know that when the kid pushes down, not only is the weight of the child trying to produce a torque, but now they're also pushing down on the board. So they're providing even more force for the torque. So honestly, it comes down to just trying to calculate, is the torque the kid providing going to be greater than the max torque the metal rod can provide? All right. And we already calculated earlier, we know that the max torque of rod is 2,250 newtons. So basically it comes down to calculating how much torque the kid is providing. All right. And when we do that, basically all we do is we just say, we do the combined force, the net force, it's 2,000 newtons. It's now both 2,000 newtons is 1.25 meters away. So if we do that, the max torque of the kid equals 2,000 times 1.25. They're both a 90-degree angle. So actually that's now going to equal 2,500 Newton meters. So in fact, the kid is providing more torque than the metal rod can provide. So this actually will cause the system to break, and it will cause the diving board to break. All right. So just once again, ladies and gentlemen, this is just simply doing equilibrium questions. It's for a rotating system, but the same rules apply. All right. So that being said, ladies and gentlemen, have a great rest of the day, and I'll talk to you later.